Let's start with Sayan Mukherjee talking about modeling shapes and fields beyond TDA.
Yeah, well, I'm not sure we're going. Anyways, thanks for the organizers. And I really want to thank the previous two speakers because they've covered probably most of the stuff that I need to cover. So thank you, Rob and Kaylin. But I'm going to talk about a problem I've been working on for quite a while with many colleagues, which is really modeling 3D images and thinking about 3D imaging and using ideas from topology and geometry to do this. So let me start. Okay, so the first point I want to make, and this is a really, I think, important point, is the genius of Darwin was going beyond the lineal perspective of thinking about shapes and organisms, in that we don't want to think about them in terms of Platonic ideals, but we want to think about them in terms of variation. And we want to study the variation of these shapes. And, you know, he was interested in evolution, of course, but and how this impacts various things we're thinking about. So another example of this is from Darcy Thompson. These are looking at conformal maps between humans, chimpanzees, and baboons. And there are reasons why he was thinking about this. But again, this idea of growth and form, going back to Thompson. One data set I will talk about, again, this is from my colleague, Doug Boyer, who's a evolutionary anthropologist, is a collection of heel bones from extinct and extant primates. And we'll talk about this in a little bit. And part of the idea and part of the reason why I started looking at some of this is because there is this more evolutionary perspective where if I can, for example, construct distances, pairwise distances between these shapes, I can start constructing phylogenetic trees. And one thing that we are working towards is doing more formal phylogenetics, not on gene spaces, but on shape spaces or in particular types of phenotype spaces. So classically, there have been three ways people have thought about shapes and shape spaces. One is idea going back to Kendall, which are he called shape manifolds, and we'll come back to that. The other idea goes back to Dupuy and Grenander, and these are based on diffeomorphisms and flows. And I will touch a little bit upon this, this approach. And this is an approach that I've worked on as well with my colleagues here at Duke, Ingrid Dobashiz and Doug Boyer. But the main approach that we're going to focus on a lot today is using ideas from integral geometry and superlevel sets, sublevel sets, and filtrations. And I'll touch on how you can try to unite these later on, okay? So starting back in the day, and this is back in the day of Kendall, one way people thought about shapes were basically you go to the British Museum, you have artifacts of interest, and you have landmark points on them. And these landmark points are all in registration. And so then what you do is you take these correspondence points and you try to define some distance or matching between them. So if I have two shapes, you know, what I can do is basically look at translations, possibly also rotations and other transformations and scalings, for example, and mod them out, right? And that's my notion of shape space. And so this was Kendall's shape space. You can think of it as a manifold, and you're basically, you know, modding these out, these transformations. There's a classic version of landmark-based analysis in a paper by Carl Pearson, where it's a bit of a grim and gruesome paper, but what they wanted to know is whether what they had, which is kind of a half-rotted version of Cromwell's skull, was really Cromwell's skull. So they applied this type of procrastinating analysis to again do that. And the paper is a little bit amusing, and the IRB protocols that, well, they did things that IRB would not allow us to do nowadays. But anyways, so that's a very early version of this. Now, what's happening more and more, and this is again something that Kaylin, you know, made clear in his talk, is we're getting beautiful, detailed databases of very detailed 3D shape structure. So this is a collection of bones that have all been scanned. These are micro CTs, and they have exquisite detail. And, you know, similarly, and I'll touch on this later on, we also have extremely detailed protein structure, both from various imaging modalities as well as from molecular dynamic simulations. Okay, so one thing you could do is you can take a bunch of points on these teeth, right? Fat them out with a little area, and then basically just do some type of optimal transport between them, right? So the actual exact algorithm here is a variation in a conformal map. You measure some variational distance, and this is really a diffeomorphism based approach, okay? And it works often. Sometimes it's a little bit tricky. So this is coming from data from David Boole's lab, who's geneticist at Florida State, and Ezra Miller has worked on this data. And the idea is when you look at some of the mutant fruit flies, they start adding lobes or losing veins, right? So things aren't, they're not diffeomorphic, right? They're actually topologically different. So what can you do there and what can you analyze, right? So the other thing that it's sometimes just nice to do is think about, a lot of times, how are the data represented, right? What is the digital format? Basically, you get a collection of vertices, faces, and edges in this case. And so it's really, really tempting to want to think about these as simplicial complexes because the raw data format is very much like this. And this is what the data actually look like, right? So again, just to iterate. So we all know what simplices are. So it's very natural to think about this in terms of simplicial complexes. And so that's one model we'll use, okay? That's just what I said. Now, let me zoom back out of this so I can use that. Yeah, okay. So this slide is pretty important, and it's not obvious why I'm giving you this slide at this point. But a more abstract notion of a shape can be defined using O-minimal structures, okay? And this is something that came and was heavily developed in logic. And what is it saying? I'm building up shapes when I look at projections, and these axis-aligned projections are well-defined. So this is really a way of thinking about tameness. And if you think about sheaf theory, this is actually a very general tool to think about this. And further, we're going to require all the algebraic sets, right? And O1 contains no more and no less than finite unions of points in open intervals in R. So this is an important idea, and this is going to be our notion of tameness. And later on, one of the reasons we'll see why we're talking about this is I'm going to be doing things, or we're going to be talking about things very related to the radon transform, and I'll show you a picture of it. But there's an inversion formula, and for that to be well defined, you need some type of control, and we'll come back to this. Another important idea are going to be constructible sets. So these are a collection of compact definable subsets of RD. These are elements of O. And similarly, we're going to talk about constructible functions. These are integer valued functions on a tame set X, right? And CFX is going to be the set of constructible functions on some domain X. If you start looking at this, you're starting to see why I'm really talking about, Euler integration, right? This is really, has a strong feeling of Euler integration, and Euler integration is going to be kind of at the heart of what I'm going to talk about today. Now, there's a picture that I want you to show you, and this is very related to the picture that Rob showed earlier, except for I'm going to first do it with fibers. And this is how I want you to think about shapes. M here is a space. Think about this as a space that things are evolving on. These are my animals, these are my organisms. They're evolving on that space, and X is, I don't know, monkey 1, monkey 2, monkey 3, let's say, okay? This is my base manifold, and then I have a fiber manifold, and I have a projection map. And what I'm gonna do, right, is think of each of the data sets, they lie on a fiber bundle, okay? And one way of thinking about this, these are my base manifold, these are the different monkeys, let's say, they're looking at. And what I'm going to put on my fibers, let's say, are a vector, which could be their teeth, right? So think about, this is actually, I'm decorating these with, in this case, teeth, right? And if everything is diffeomorphic, I can do parallel transport to move between these two, and I can construct this type of fiber bundle view of shapes, okay? Now, one of the things that we're going to start doing, and one of the points that I wanted to make is that we want to make something a little bit more general because not all my shapes are going to be diffeomorphic, right? And so is there a generalization of this? Can we think about these as stocks instead of fibers? And can we think of this as a more sheaf theoretic perspective? And I will touch on that. Okay. So integral geometry and representation. Okay. I want to model shapes without requiring landmarks or diffeomorphisms. I want a representation that I can use more standard statistical methods. I want this transformation to be injective. The transform space to be nice, maybe a matrix, maybe something that's manageable. And one of the things that's going to be important is I want to be able to pull back from this transform space. So I want to be able to invert it, right? So I want a transformation and its inverse. Okay. There are two summaries I'm going to talk about. One can construct others. One's the Euler characteristic, and the other one's persistent homology. I'm also going to talk about a variant of the Euler characteristic, which we use for fields, which we call the lifted Euler characteristic. I just put this in there because it's a pretty picture. Okay. I think everyone knows what the Euler characteristic is, so I'll go by this. So the other idea we're going to use is a height function. And I remember, for me, the first time I was reading about a height function was in work by Yu-Su Wang and John Hare and Herbert Edelsbrunner, and they're actually using it for protein structures. And I will actually come back to using the height function later on in this talk for protein structures, but we started using it for bones. And so you're basically just filtering and looking at sub-level sets of the shape from different directions, right? So you can generate an Euler curve that looks like this. And in real life, because we feed everything into a computer, we actually discretize it, but we'll get to that. Okay. And as you all know, this is also picking up critical points, right? That's what this is doing. And this is a smooth version of it. You basically, I integrated it and zero meaned it. Okay. You can skip this. This is persistent homology. I don't know why I put it in here. Everyone knows this. Okay. Definition of a persistence diagram. Okay. You have the notion of a Wasserstein metric. Now, stability on diagrams was important and useful, but one of the things I was also clear is it didn't go the other way, right? You can't get the function back from the diagram, and that's something that I will talk about. Okay, so what's one way of thinking about the Euler characteristic transform? It's a map from the sphere of to the space of Euler curves, right? That's one way of thinking about mapping in each direction of the sphere, get back a constructible function. Another way of thinking about it, take your shape, go in direction V up to, level set T and look at the sublevels. Okay. The smooth one is just what I told you, integrated. So this is mapping things to functions in L2. And then again, you can define the persistent homology transform similarly. You're going from the sphere into diagrams. And there's a relation between these. This is something that Rob has in one of his papers with his students, and Kate and Justin and I have as well. And so they relate to each other in that they commute. Okay, not surprised. You can define distances between diagrams. Similarly, you can define distances between curves. So that lets you start doing some analysis. And these types of integral transforms, right? I think one of the earliest and most common is what is the radon transform. And what is that? You basically take an X-ray and you pass it through a device and you get a projection, from all these different angles, and then you want to have to recreate it, right? So there's that inversion formula. And one can ask, under what conditions is this a well-posed problem, and can I reconstruct? And there's a beautiful theorem by Shapira. This is Shapira's inversion theorem. And what he basically is doing is using these O-minimal structures, right? And ideas about Euler integration, the constructible functions, to show that, that it is invertible. Okay. And again, that's why we kind of started with this O-minimal idea. So initially, Kate, myself, and Doug showed that you have invertibility in dimension, 2 and 3. And then later on, Justin, myself, and Kate, and then Rob and his students basically showed that in any dimension, there is this notion of that it's an injective map, that you don't lose information. and again, very, very strongly using ideas like Shapiro's inversion theorem. Okay, so there's another idea here, which I think is really, it turned out to be practically useful. At first, we thought it was just theoretically interesting, which is, let's say, one of the things people do when they analyze shapes is the first thing they do is you take your shapes and you basically have to orient them. So basically you have to rotate them so they get oriented to each other. Now, if you have a set, how do you do it? It's somewhat annoying. What you do is you first do it pairwise, right? Then, for example, you can construct a minimum spanning tree and then redo it on the minimum spanning tree and do this until you basically stop iterating. But the point is, to do this, people always need a correspondence map. Now, the question is, can you do this without having some notion of a formal correspondence map, or at least a correspondence map as you would think of it in the case of the diffeomorphic setting, right? So one thing you can do is you can take this Euler characteristic transform, think about the directions as random. So I get a collection of random directions here, a collection of random curves here, a collection of random curves here. And then basically what I can do is I can just ask, right, is there some type of optimal transport between these two, right? So if I were to, in some sense, rotate them, can I get them back, right? So you can actually start thinking about this distributionally, right? And in that sense, you actually don't have to necessarily pre-align them, or you can use this theorem itself to do the alignments themselves. Okay. You can basically think about the distributions of the Euler curves. Okay, so there's this question of how many directions do you want to sample? And initially, empirically, we did 162 and 3D over 700. And this empirical question will come back. But we started wondering, is there a theory for this? How many directions do you need? Okay, and there's this beautiful paper by V.I. Arnold, where he says, if I take a bunch of functions, right, and I tell you where their critical points are, how many homological different functions are there, right? And he gives a closed form solution for it, which is amazing. Doing this in dimension greater than 1 is going to be really tricky because these are based on orderings. So this is what we did. We considered a moduli space of shapes. They're in some dimension D. I have some minimal angle delta, or this is going to be curvature, and I'll tell you what it is in a second, and some control on the number of critical points if I sweep out in a cone delta. So those are going to be the 3 parameters, right? And so this is what I told you. At each vertex, there's a lower bound and curvature. And if I move in any direction, right, I have some, and I look at a little ball, I have some control of the number of critical points. This is more formally what we mean by curvature. Okay. Again, these things are discrete, so it's really looking at this little ball. And the point is, if something is super flat, it's very hard for me to tell one thing that's super flat from another thing that's super flat. Okay. Now, before I to give you the theorem, let me tell you something, okay? What is this doing? Again, you're stratifying a sphere, okay? And this is what's going on in one direction. And this is like my little ball. And the point is, if I have one Euler curve here, if I move just a little bit, right, I should be able to tell you again what the Euler curve looks like. So there's going to be a linear relation between the Euler curve here and the Euler curve here. So really you're taking the sphere and you're stratifying it into parts, into some discrete number of parts. And this is a bound on that stratification. Okay, so if I have this moduli space of shapes, I can basically tell you how many directions I need to be able to tell apart any 2 shapes in this moduli space, which is kind of interesting, okay? So this is another picture of how you can think about the persistent homology transform. You have a constructible set and you're just tracking the cohomology of the shape filtered along a direction V. Okay. Now, and this is recent work, we're writing it up. This is with grad student at Duke, Shreya Arya, and with, again, with Justin and myself. And the idea there was, I showed you guys a picture early on of this fiber bundle notion of a shape, right? Now we wanted to think about it more from a persistent homology transform perspective. So this is a more sheaf theoretic perspective. So I have a category. These objects are constructible sets. I have relations are included conclusions. This is Grothendieck's site. And to each object, I'm attaching a persistent homology transform. Okay, so now the point is you have a functor from M to the PHT of M, and this is a sheaf. And so this is one way of thinking about constructing a shape space using sheaves. Okay, there's a sheaf or a gluing axiom. The PHT of the larger space, you can compute from smaller pieces of the shape. This is interesting because it starts to suggest that you can distribute things. Now, one of the things that's interesting is when these shapes are these flat simplicial complexes, you only need 0-degree information. So for these types of data, these micro CT triangulated data in 3D, you actually only need degree 0 information. Okay, this is currently a conjecture, but it should be not a conjecture very soon. And I'm missing something here, but okay, so it's not true for any general arbitrary constructible set, but then you can basically approximate any nice shape. You can approximate by a PL shape. And again, we're finishing up this theorem, but this is actually a straight up application of the work done by Nyogi, Schmale, and Weinberger, right? So that's an idea. And again, in the sheaf theoretic construction, there is an open set perspective of these shapes. Okay. Now, moving back to more statistical ideas, one of the things that's neat is if I give you a bunch of shapes, I can turn them into these smoothed Euler characteristic transform curves. And each of these, right, again, if I discretize it, I can basically start putting probability models on it. And so I can actually define likelihoods. This is a very discrete version using the matrix normal. And later on, we'll do a more fancy version, which I'll talk about in more detail, is you can basically put a Gaussian process on these shapes. So you can start doing non-parametric regression, and we'll talk about that very soon. Okay. So one of the early applications is we took the persistent homology transform and we measured pairwise distances between these heel bones of these 106 primates. And what you see are, these are the great apes. Gibbon is a lesser ape. This is a spider monkey. So these are old world monkeys, although the spider monkey is not. These are all new world monkeys. This is an extinct one, and these are all lemurs. But the point being is you really start getting back what people believe these taxa should be, right? And that's kind of interesting. I'll skip this. And this slide, I think, is a very interesting question that somehow I don't feel has completely been resolved. And so the question is, if you apply Kendall's idea versus a diffeomorphism-based approach versus the persistent homology-based approach, which one is the best, right? And I mean, that's going to depend on many things. And so, you know, visually this one looked good, but there's also a very basic mathematical question here, which is, I suggested to you a sheaf theoretic construction of shape space. Early in the talk, I gave you a fiber perspective, and a very natural question is, first, qualitatively, when your shape space consists of things that are diffeomorphic, right? Will the sheaf theoretic construction, you know, just fall back to the fiber construction, right? Will those constructions be somehow equivalent in a qualitative sense? And then one can ask also in terms of a quantitative sense, if you define the quote unquote correct distance measure between these, again, do they align, and how does that go through happening, right? And this is one start to asking this question, you know, when things are not necessarily diffeomorphic, how can I start rigorously defining distances between shapes? And this is something Rob and students have thought about using Minkowski functionals, but I think there's still a lot to do there. Okay, now something, a more practical application was in medical imaging. And what do we have here? We have, well, we have a brain, and this is a brain tumor. And you can get data where you have gene expression. So you have matched data on 92 patients where you have both MRI data as well as genomic data from the Cancer Genome Atlas. And we have morphometric features. These are features that radiologists and oncologists decided on. It's a list of 212. These volumetric features are pretty trivial. And then we can basically construct topological features using the smoothed Euler characteristic transform. And we can try to predict two things. One is disease-free survival, and the other one is overall survival. Okay. I think this is what I said. And we can even try to ask which one of these features does the best. Okay, so we basically, this is just how we're representing them. This is taking different directions from these slices. And then we stack these all as a feature. And we use something called a Gaussian process or a kernel model. And this is just what I'm showing you. At each data point, you're putting a little function and you weight it. And this is very simple in that you can do closed form regression. We've also done this using neural networks, but I won't go into that. And then we used linear kernels, and we used a Gaussian kernel, and we used a Cauchy kernel, because this one sometimes does a little bit better. Anyways, bottom line is what we found is the best for performance was using the these Euler characteristic transforms. Now there's an interesting question here. Why would topology or multi-scale topology tell us something about disease-free survival? Now, one thing that surgeons do know is if you have a tumor and it's scattered into a lot of little bits, so Betty zero is large, that is often bad, right? That's one thing we do know. People know when you look at, again, surgeons, when you look at breast tumors and you have a tumor on the inside is dying, right, is more hollowed, which is, again, telling you something about Betty 2, outcome is often good, right? So there's something that's still open, which is how do we relate these features to what's happening at the molecular, right, level and the physiological level in this tumor is. And there's, I think, a lot of interesting and open questions there. Now, there's this question of what parts of the shape are most associated to variation in a trait, right? So is there some notion or analog of variable selection or subshape selection that we can apply? And you can do it for various cases, but we'll first apply it to the problem of again, shapes, okay? And this is work with one of my former students, Lauren Crawford. He really ran a lot of this. He's at Brown and Microsoft now. And so this is something we call Sinatra. So what's the idea behind Sinatra? Let's say I have two different classes, okay? What I'm gonna do is I'm going to basically filter through, this is gonna be my topological feature, okay? And so now what do I have? I have a bunch of curves, let's say for, category 1 and category 2, okay? And I'm gonna tell you, I'm gonna come up with an algorithm that tells you which parts are the most different, right? Which elements of these curves are the most different, okay? Now, once I have that, that's all well and good, but I actually initially wanted to tell you what's going on in 3 space, right? Which parts of these shapes are the most different. So then we have to map these variables back onto points in 3 space, okay? And this lets you visualize the enrichment or visualize which parts of these teeth are most variable, right? So I'm going to talk you through how we do this, okay? So I already told you how I represent the shapes, okay? So we use a statistical model. That's just my Gaussian process. You could have also used a neural network. So now there's a question of how do I get some type of notion or metric of how good these features are, okay? So typically, like I said, we wanted to do this for nonlinear models. And for a linear model, it's easier to do because if you're doing regression in a linear model, you have a coefficient, you have these beta hats, and these tell you the effect size, in some sense tell you how relevant each of the features are. Now, it turns out you can do something similar in nonlinear models, and I won't get into the details of that if people want to hear about it, I can tell them more, but there's a way of getting some notion of an effective, the analog of an effective size. Okay. Now you have those, the question are, how do I select them? How do I know which of these beta tildes are the most important, right? And again, one of the things I just wanted to tell you is the way we did it was using a Bayesian method, and that the utility of that will come up in the next slide. But the point is, I can get a lot of these. I can get a full distribution of these beta hats. Okay. So one way you can try to figure out what is a useful variable is something that you can do, well, a while ago, people did, well, one person did this. You take a team, right? You take one of the players off of the team and you see how well they do, right? This happened with Mike Jordan, X years ago. And you can basically use that notion to figure out which of these variables are the most important. So what you can do, because I have this distribution on these betas, I can compare two things. I can just marginalize out one of the variables versus compare it to this conditional, okay? And then I can look at the KL divergence between these two. And just for simplicity, I can pretend these are all normal, so I can do this very easily. And then, okay, once I have these, right, what do I know? It's 0 if it doesn't matter, right? If nothing changed. And so then I just normalize them, okay? And we call this the relative centrality or rate statistic. And what's really nice about this is you can apply this to almost, if you can get something like a posterior, you can compute this. And so there are even neural networks where you can actually do this on, which is kind of cool. Okay. And then you can think about significance as when is it, bigger than 1 over p. So that gives me evidence of association. Now, how do you project it back? So that picture I was showing you, right, in terms of the stratification, right, where, and if I went in one direction and if I slightly move it in another direction, there's a linear map, right? So that idea is at the heart of getting that shape back, okay? So again, directions near each other will share in similar information. So the reconstruction algorithm is going to take the following steps. Pick a cone, the set of directions for each, okay? So you're going in a direction, okay? Another way of thinking about, well, I'll show you in a picture in a second. Let me actually just go back. Yeah. So what's going on? You have a shape, right? And I have a direction, and I know how far in that direction is it significant, right? That's basically, that's what I'm getting back from the topological, variable selection part. Now what I need to do is take those and get back the actual point in 3 space, right? Now, if you do this for a very tightly oriented cone, you can basically just start drawing this in, basically discretizing and getting these sets of points back. Another way you could have done this is basically trying to solve this problem, okay? Where you're trying to get the third coordinate, okay? So one of the things that was really kind of interesting when we worked on this is how do you even do simulations, right? To know things are going right? How do you construct these different classes, and how do you know your algorithms is actually working? So one of the things we did was we took a shape, and then we took some ideas that people had done in graphics where we could actually character them. So we could like build extra little nodes, make them smaller, so on and so forth. And then we could run Sinatra on them and actually look at what was actually different, and are we getting back the things that we suspected, right? And then we did many simulations. We looked at ROC curves, try to really carefully understand this. And then the real data set we had was these different genera, right? And well, let me show you the tree. So this is this Tarsius and Winnow, something about this little cusp on it. And these are different, going further and further phylogenetically. And we started asking questions about if we were to run this, right, pairwise, what would they look like? What would the differences look like? And are there more as we get further away? And again, this is something that we saw in, as an example. So one of the things that Lauren's been working on and I've been involved with is this idea of combining these shape statistics with genetic information and other intermediate informations to really in deep neural networks to try to really understand how the genotype phenotype variation is occurring. Okay, we recently just posted a paper on bioRxiv on adapting Sinatra to protein structure. So this is something that Kalen showed, right? That you have these types of molecular dynamic simulations and you can fill it out and then you get these very nice folds, right? That start explaining things. So I'm just gonna give you the guts of it is that we input protein structures, okay? Let's say this is your wild type or mutant. We get atomic positions. From that, we basically triangulate it, get a mesh representation, right? Do a filtration, which is basically some type of Euler characteristic. We apply a slightly different type of Gaussian process to this. And then we use the really very, very similar reconstruction scheme, and we get these colors. And these are where you have the greatest variation in from the mutant to the wild type. And again, because here you can do molecular dynamic simulations, you can generate a ton of these. And this is just one example. This is a beta lactamase, and this is the wild type is a particular mutation. And so this is if you look at the whole the whole protein, and then you can kind of zoom into different parts, and you can look at different loops again. But the idea is what we were doing with shapes, you can start thinking about also doing with protein structures. And the last example is we have a 3D field. So now we're no longer looking at hard tissues, right? Which the CT scan of a bone, you're looking at soft tissue. This could be MRI, it could be, some type of 3D field. And we want to do something very similar to what we did for the shapes for this. So this is a problem that people have worked on. I know Rob has worked on with Urea and Euler integrals for continuous valued approaches. And we took a slightly different approach, and I'll explain it. So one idea, is make it discrete, integrate against the curvature, right? Do like a weighted Euler transform. So what we did was we did what we called the lifted transform, right? And this is very much in the spirit of back in the day, what people like Keith Worsley or now even Robert Adler and Jonathan Taylor did. So what we do is you have this 3D field. I'm going to go in a direction, right? But the first thing I'm going to go is before I sweep through in this direction, I'm going to look at super level sets in terms of function values. So you're looking in a particular direction, you look at super level sets in terms of function values, and you construct and you basically use that object as your simplicial complex, right? And then you compute the Euler characteristic transform of that. So before what you had was you had a vector, right, for each direction. Now you have a vector for each direction and value, and that's our lifted transform. Okay. Under this O minimal structure, it's injective, invertible. Okay, it's a stratified map. Okay, and there are interesting things here as well, which is when you try to compare these, right? Do you want to compare with the values, without the values? So like you want to marginalize out in particular directions. I just want to show you one result with this. So this is a breast cancer imaging data set. It's a MRI data. And this is one of my colleagues at Duke. They ran this using a machine learning algorithm. And this is very recent. The student working on this, Henry, finished this up a week ago. So we're still kind of cleaning it up and trying to make it a little bit better. But the point being is using a pretty simple classifier, again, a Gaussian process, and these lifted Euler characteristic transform features, we're getting very similar performance to the machine learning algorithm for trying to tell apart these different types of clinical, clinical or genetic phenotypes for the breast cancer. So that again is something interesting. And it's just really starting, so there's a lot to do here. Let me state one more thing. We're writing up this paper right now, and to be honest with you, what we're working on really writing up initially is more of a math paper, which is with one or two examples, and this is the example. We're going to start actually trying to make this much more statistical and figure out how to set these parameters more nicely, and do simulations and things like that. So that's going to happen over the next few months. I think there's a tremendous amount one can do thinking about things in terms of Euler integration and sheaves that we really haven't done, and we should. There's a dictionary version of this. One of the things that we worked on, and there's a lot to do here. This was not with the sheaf perspective. This was with the fiber perspective, and this is work done by a former grad student, Duke Shanshan, who worked with Ingrid and myself and Doug. And what we were able to do is define some type of Gaussian process on these bundles. And there we could incorporate evolutionary models to do formal tests, like whether something was Ornstein-Uhlenbeck, or we believe it's more like a burst structure or just Brownian motion. This suggests another project which we've been working on, which is how to think about defining Brownian motion and things like Gaussian processes on sheaves. So this is this idea of putting stochastic processes on sheaves. There's a very, very evocative fact, which is if you want to put, let's say, a Gaussian process on a manifold, it can be tricky to do if you do the most obvious thing, which is write e to the minus some constant times the geodesic distance, because that may not necessarily be positive semi-definite. Now, there's another way of defining Gaussian a kernel on a manifold, which is by you define a stochastic differential equation on the manifold, and it has two elements. It has a Laplace-Beltrami operator, and it has Brownian motion. Okay, you solve that SD, and it gives you a kernel that's semi-definite, positive semi-definite or positive definite. Now, it would be very interesting to do this in the context of sheaves, right? And why? Because we can now start thinking about defining kernels that are positive definite out of these very rich topological summaries. We've been working related is work on Ito calculus on manifolds without parallel transport. I'll close soon, but there's a very, okay, I asked this question, how many directions do you need, right? And I gave some answer for it for a moduli space. This also, there's a very practical version of this problem, which is the following. Let's say I want to have a patient, I want to do CT scans on them just to see how things are changing, right? But I also have a radiation budget, right? And that I can't radiate them too much. So one question that you can ask is, can you come up with a minimum number of directions and tell me what those directions are if I a priori gave you a set of objects, right? And what procedure would you come up to do that, right? And so that's a very practical question that we are working on. And again, there's this fiber bundle sheaf theory for shapes, and again, integrating the physics and the imaging. And these are people who talked to us. There's some people who gave us money, and I will stop.
Thanks, Cheyenne. We have like 5 minutes for questions. So if you put it into the into the chat box for a question. Kaylin.
Yeah, thank you. This is very interesting talk. So I was wondering that when you are doing this comparison, do you need to do an alignment first? For example, you have so many structures, right? For example, you have like shape like this. Do you need to like align them first so that because you have to check the transformation in each directions.
Right.
So yeah.
So Kaylin, this is a great question. So when we wrote the paper for the shape part, not the protein part, because we just finished, we said that we could do, we had this entire method for analyzing shapes without requiring correspondences, right? And one of the reviewers said something very reasonable, which he said, I don't believe you. And the reason I don't believe you is that initially you had to align them. And for that, you had to use correspondences, right? So then what we did was we told the reviewer, actually, that's not true, because we aligned them using that by thinking about the directions as random. So a random collection of shapes and then matching those. So basically coming up with a rotation to match. So that's what we ended up doing. But yeah, we have to pre-align them before we do the analysis.
I see. Yeah, just very quick, another question. So for this final genetic tree you are building up, you can use the gene information, right? The genomic one, and then
that's what we're trying to do.
Yeah,
so, that's what we're trying to get to.
So is there any ground truth you think the gene-based gene and the final genetic tree from gene is more plausible, or from the structure, this phenomenological one is more plausible? How you have this ground truth?
I think this is really hard, right? And that's one of the things, one of the reasons why I want to build up this type of theory for something like a stochastic process on fibers or on sheaves is to be able to do those detailed simulations and actually be able to and understand this. And the other thing that I'll tell you is, like, a lot of my colleagues who do geometric morphometrics and look at these phenotypes, they're insanely adaptionists, right? And getting like a really rigorous, selection coefficient and things like that is done so little in that literature, and it's tremendously frustrating. So really one of the things we're trying to do is build up that math and do those simulations to try to get at that, because I have no idea what ground truth is. Right? Maybe for some of the protein stuff, it's a little bit more doable, right? Because shorter evolution, we know a little bit more what's going on.
Yeah. Yeah, very interesting topic. Yeah, thank you. Yeah.
Wojciech.
Yeah, I guess maybe I'm asking the same question as Kellen. So okay, I have a bunch of teeth. I do these homology transform. I'm project get the let's say Euler characteristic or homology. Now I would like to look at that information and build this tree. Look at the evolution. How do you do that?
Okay. So unfortunately, I did not add those slides, but I'll give you a picture. Actually, I can do it. I can do something here. I can help you. Okay, so this is what I want you to think about, okay? I'll do it for a fiber case, and then we can kind of talk about how to extend it, okay? So what I'm gonna do is, on this base manifold, I'm gonna put a stochastic process down, and that's my model, right? That could be Ornstein-Uhlenbeck, right? That could be a burst model, that could be Brownian motion. That's my evolutionary model. It has that evolutionary parameters. I know in theory what the distance is, the time to the last ancestor for the two of these, so I can plug that in there, okay? Now, because fiber has an independence construction, right? I can think about a product structure between the stochastic process and the kernel going on down on the base manifold versus what's going on the bundle, okay? And so on the bundle, let's say I just use some Procrustes distance or something that's well-defined, define the kernel, right? And then what I do is I take all my evidence, I marginalize out what's going on up here, right? And then I can compute something like a base factor or some type of information as a ratio, right, between, let's say, two models. And so I can now tell you how much more likely, let's say, the Ornstein-Uhlenbeck is than the Brownian motion, okay? So that is what we're trying to do. And we know we have some idea of how to do this for the fiber setting. This is extremely open on how to do in the sheaf setting, because defining that stochastic process on a sheaf, right, and positive definiteness it's tricky. Okay.
All right. Thank you.
So I think we're out of time for questions. I know that Jürgen had one. Maybe you can chat that to Sayan. Thanks, Sayan.
Yep.
And,
thanks, everybody. Jürgen, happy to talk some other time.
Of course, yeah. Very interesting talk.
Thanks, everybody.
So